Good evening, everyone. Welcome to a tutorial on analyzing Fourier transform using MATLAB. I am Priyanka Shukla, and I will be presenting today's session. With me, I have Shanti and Shakdhara, who will be moderating the chat. We are from MathWorks, the makers of MATLAB and Simulink, our key products. MathWorks is the leading developer of mathematical computing software for engineers and scientists. Here are some industries where our tools are being used extensively: aerospace and defense, automotive, biological sciences, industrial machinery, to name a few. Here's what we will cover in today's session. We'll start with the objectives. Next, we will see the MATLAB functions for the Fourier transformation. In today's session, we will explore how to analyze electromagnetic wave signals by leveraging Fourier transform techniques using MATLAB. We will demonstrate key functions such as FFT, FFT shift, IFFT, and FFT2, focusing on how they can be applied to identify frequency components, visualize interference, reconstruct signals, and analyze multidimensional data. We will wrap up the tutorial by summarizing the key takeaways, followed by a Q&A session where you can ask questions or clarify any doubts. This session is designed to showcase how MATLAB tools can be utilized to implement techniques like Fourier transform rather than delving into the underlying theoretical principles. In this session, we will perform Fourier transform on signals using MATLAB functions and visualize frequency components of signals using MATLAB. Fourier transform is a mathematical tool that decomposes a signal into its constituent frequencies, allowing for the analysis of signals and systems in the frequency domain. It has numerous applications across fields, including engineering, physics, and signal processing. In signal processing, the Fourier transform is critical for breaking down audio signals into their frequency components, enabling techniques like audio compression, noise reduction by filtering unwanted frequencies, and speech recognition systems that analyze vocal patterns in the frequency domain. In image processing, the Fourier transform is used for analyzing spatial frequencies in images, enabling tasks such as image compression by retaining significant frequency components and discarding less important ones. In communications, the Fourier transform underpins modulation techniques like AM/FM by converting signals in between time and frequency domain, assists in designing filters to isolate specific frequency bands, and helps in radar and sonar signal analysis by identifying target signatures from the reflected signals. In medical imaging, the Fourier transform is essential for reconstructing images in technologies like MRI and CT scans, where data collected in the frequency domain is transformed into detailed images. It is also used to analyze physiological signals such as ECG and EEG. MATLAB provides inbuilt functions to perform Fourier transform operations, making it easier to analyze signals in frequency domain. In today's session, we will focus on FFT, FFT shift, IFFT, and FFT2. The FFT function computes the fast Fourier transform of a signal. It's a primary tool we use to transition from time domain to the frequency domain, helping us break down a signal into its frequency components. This is particularly useful for identifying noise or interference in communication systems. After applying FFT, the frequency components are arranged from 0 to the Nyquist frequency and then back to the negative frequencies to 0. This can be difficult to interpret visually. So, we will use the FFT shift function, which rearranges the data to the center 0 frequency component, making it much easier to interpret symmetrical signals and analyze positive and negative frequency components. Once we have analyzed or processed the frequency domain data, we often need to reconstruct the original time domain signal. For this purpose, we will use the inverse fast Fourier transform function, that is IFFT. This function allows us to reconstruct the original time domain signal, ensuring the signal integrity is preserved after the frequency domain processing. In some advanced scenarios, such as radar imaging or multidimensional signal analysis, we work with two-dimensional signals. In such cases, we can use the FFT2 function, which extends the Fourier analysis to two dimensions, enabling us to analyze spatial and temporal variations effectively. Now let's see what we are going to do in today's session. The electromagnetic signals play a critical role in modern communication and radar systems. These signals are often made up of multiple frequency components that carry essential information. However, they are highly susceptible to noise and external interference, which can distort the signal and reduce reliability. When analyzing these signals, the traditional time domain methods fall short. They cannot effectively reveal the individual frequency components within the signal or clearly assess the impact of noise. This makes it challenging to pinpoint issues and improve the signal performance. This is where the frequency domain analysis becomes essential. By breaking the signal down into its constituent frequencies, we can easily identify noise and interference. This separation allows for better filtering, ensuring signal clarity and reliability in critical applications like wireless communication and radar detection. But the challenge lies in effectively processing these signals. The goal is to extract valuable frequency domain information while enabling effective noise filtering and enhancing the overall signal quality. Throughout this session, we will see how MATLAB tools and techniques will help address this challenge effectively. So, we will first perform the FFT analysis to identify individual frequency components and detect noise or interference. The purpose of this step is to provide insights into the signal's behavior, directly addressing the need for frequency domain analysis. Then we implement the FFT shift, which explains that visualizing the frequency spectrum using the zero-centered approach makes it easier to interpret the positive and negative frequency components, which is critical for analyzing symmetrical signals or interference. Then we will reconstruct the original signal using inverse fast Fourier transform or the IFFT function to validate the Fourier transform process and ensure that the signal retains its essential characteristics after analysis. Now, let's go to the next part of the tutorial, where we will practice analyzing the Fourier transforms using MATLAB. I will request the participants to mute themselves. If you have any questions, please post them in the chat. So, for this purpose, my colleagues will be sharing a work life script which has placeholder codes. During the session, my colleagues will post the relevant codes in the chat window so that it is easier to follow along. At the end of the session, we will share the solution live script, which you can use for your future references. To get started with this hands-on activity, please download the work live script shared in the chat. You can open the file in MATLAB Online provided for this course. To access the MATLAB Online, go to the NPTEL course page and navigate to the MATLAB Access section. Then click the link provided in the third step. If you have not accessed MATLAB Online before, please complete the 3 steps mentioned on the MATLAB Access page. Once you have downloaded the live script and opened it in the MATLAB Online, please put a thumbs up in the chat window. I repeat, if you have downloaded the work live script and opened it in MATLAB Online, please put a thumbs up in the chat window. In case you're not able to access the MATLAB Online provided with this NPTEL course, please download the work live script and open it in any licensed MATLAB Online or MATLAB desktop version. Once you have opened the live script, please put a thumbs up in the chat window. I hope everyone has the live script open. So in today's tutorial, the first step in analyzing the electromagnetic wave signal involves transforming the signal from the time domain to the frequency domain using the fast Fourier transform function, that is the FFT function. This enables identification of the dominant frequency components, which are crucial for detecting potential interference or noise. So, to perform this analysis, we need to sample the signal at an appropriate frequency, that is the sampling frequency Fs, to ensure it captures all significant components of the original signal. The time vector t represents the time instances at which the signal is sampled, and the frequency vector f represents the corresponding frequency after applying the FFT. So, for today's session, let's consider a signal composed of two sinusoidal components, one at 15 Hz frequency and other at 20 Hz, having a sampling frequency of 50 Hz. So, for that purpose, please add the codes in line 1 to 4. In this, we will be adding the sampling interval, sampling frequency, time vector, and we will also define the signal. So, for the sampling interval, please enter Ts is equal to 1 by 50. We are defining the sampling interval as Ts is equal to 1 by 50. The sampling frequency is defined by the variable Fs, and we are entering the value for the sampling frequency as Fs is equal to 1 by Ts. For the time vector, we are defining the variable small t, which is defined as and then let's define the signal, which is composed of two sinusoidal components, one at 15 Hz and other as at 20 Hz, as x is equal to sine of 2 pi by 2 pi 15t and plus sine 2 pi 20t. I hope you have entered the codes from line 1 to 4. Please put a thumbs up if you have completed till this step. I repeat, the first step is to transform the signals in time domain to the frequency domain using the FFT function. So for this purpose, we are considering a signal which has two sinusoidal components, one at 15 Hz and another at 20 Hz, and both are sampled at a sampling frequency of 50 Hz. For this purpose, we have entered the values of sampling interval, sampling frequency, time vector, and we have also defined the signal. I hope you have added the first four codes in the placeholders. Now, navigate to the Live Editor tab in the MATLAB toolstrip and click on Run section. I repeat, navigate to the Live Editor tab in the MATLAB toolstrip and click on Run section. I hope you were able to complete till this step. Please put a thumbs up in the chat if you have completed till this step. So, once the section runs, you can see a time domain signal which has two frequency components, one at 15 Hz and other at 20 Hz. However, since the signal is in time domain, it is difficult to compute the frequency components. For this purpose, let us now transform this X signal into Fourier transform using the FFT function. For that, enter the code in line number 5 for Fourier transform of the signal as y is equal to FFT of x. I repeat, once you have seen the time domain of the signal, we are now going to compute the frequency components of the signal by applying FFT function. For that, please enter the code in line number 9 as y is equal to FFT of x. Once you have entered this code, we will now plot the magnitude of the transformed signal as a function of frequency. For this, please navigate to the live editor in the MATLAB toolstrip and then click on Run section. I repeat, navigate to the live editor tab and click on Run section. You can see in the plots, we have two frequencies at 15 and 20 Hz. But we also can see two more frequencies. We will analyze these two additional frequencies in the next step. I hope you were able to follow along and have completed till this step. Please put a thumbs up in the chat window if you have completed till this step. So currently we have plotted the magnitude spectrum, which is typically used to visualize the power of each frequency component. And since y contains complex number, we can plot the squared magnitude, that is the absolute squared, to represent the power spectrum. So in this section, let's add code at line number 15 to compute the power spectrum. Once you have entered the line of code in line number 15 to calculate the power spectrum, go to the live editor and again click on the Run section to see the power spectrum. In signal processing, the power spectrum is often visualized in decibels, that is dB, for better interpretability. So let's convert the power spectrum into power in dB. For that, please add this particular line of code at line number 20. Once you have added this particular code, go to the live editor and click on Run section to see the power in dB. So with this, we have completed the first step in which the aim was to convert a time domain signal into a frequency domain signal. And for that purpose, we have used the FFT function. Next, we are going to use the FFT shift for rearranging the Fourier transform output so that the frequency component is centered in the spectrum. This particular visualization is helpful for analyzing symmetrical signals or interference as it places negative and positive frequency components on either side of 0. So there will be a difference between the FFT and the FFT shift results. When we plot FFT directly, we can see the frequency components are arranged from 0 Hz to the sampling frequency. However, this layout can make it challenging to interpret the spectrum, especially for signals with symmetrical frequency components. By using FFT shift, the frequency range is shifted from minus fs by 2 to plus fs by 2, centering the 0 frequency. This makes it easier to visualize the frequency components symmetrically around 0. It also highlights both the positive and negative frequencies. So, for this purpose, let's add the codes to the lines 27 and 28, where we are first defining a zero-centered frequency vector and then calculating the centered FFT result. Please add the required codes of line in line number 27 and 28. In this particular section, we are going to show the results of the plots with and without the FFT shift so that you can visualize the difference of the FFT shift function. I hope you have added the codes of line in 27 and 28. To visualize the results, go to the live editor and click on the run section. I hope you were able to complete till this step. Please put a thumbs up in the chat window if you have completed till this step. So you can now see two plots, one before the FFT shift and other after the FFT shift. In the first plot, the x-axis represents frequencies from 0 to 50 Hz, that is the sampling frequency. This layout is useful for applications where only positive frequencies are of interest, but it can be harder to identify symmetrical properties or interference. In such cases, we will apply the FFT shift, and after the FFT shift function is applied, the x-axis is rearranged from minus fs by 2, that is minus 25 Hz, to fs by 2, that is plus 25 Hz. So this layout centers the 0 frequency component, making the positive and negative frequency components easier to interpret. For signals with symmetrical properties, this representation provides a clearer view of the spectrum. I hope you were able to complete till the second step. Please put a thumbs up in the chat window if you have completed the second step. Now, let's move to the third step, where we want to reconstruct the signal. The reconstruction is a crucial step in signal analysis, showcasing how the frequency domain information can be transformed back into the original time domain signal using inverse fast Fourier transform, that is IFFT function. This step not only validates the accuracy of Fourier analysis, but also emphasizes the significance of proper frequency vector definition. The frequency vector defines the mapping of frequency components to the Fourier transform. Incorrect or poorly defined frequency vectors can lead to mismatched or distorted reconstructions, undermining the fidelity of the analysis. For this purpose, we have already defined the correct frequency vector as F. And now let's add a line of code in line number 47, where we will reconstruct the signal. For this, we are defining the variable x reconstructed as IFFT of y. Once you have added this particular line of code, go to the live editor and click on the run section. In the reconstructed signal, which is represented by red and dashed line, you can see that it perfectly overlaps with the original signal that is shown in blue color. This confirms the accuracy of Fourier transform and its inverse. This ensures that the signal's characteristics are retained. I hope you were able to complete this step. Please put a thumbs up in the chat window if you have completed the third step of signal reconstruction. Now, let's see one more step in case you want to do a signal analysis of a two-dimensional variation, which is possible in advanced communication or radar applications. In such cases, the signals will have spatial and temporal domains. For such applications, you can use the FFT2 function, which is an extension of the FFT or the one-dimensional Fourier transform. For this purpose, let's consider a 2D sinusoidal signal composed of two frequency components along the x and y axis. I've already added the code, so just click on this code and go to the live editor and click on the run section button. Now you can see two plots here, the original 2D signal and the 2D frequency spectrum. The first plot shows the 2D sinusoidal pattern in the spatial domain. This is the signal in its raw form, combining two sinusoidal components along the x and the y axis. In the 2D frequency spectrum, which is the second plot, you can visualize the frequency components of the 2D signal in frequency domain. There are four distinct peaks in the plot, which represent the positive and the negative frequency components for each axis. The peaks on the horizontal and vertical axis correspond to the frequency along the x and the y directions. The symmetrical nature of the peaks is due to the Fourier transform representation of both the positive and the negative frequencies. This 2D frequency spectrum highlights how spatial variations in electromagnetic signals, that is, radar sweeps and antenna patterns, can be effectively analyzed. The presence of the distinct peaks ensures that the signal's essential frequency components are retained. Engineers can use this information to isolate dominant frequencies, filter out noise, or optimize system design for better signal clarity. By understanding the 2D frequency domain, engineers can address challenges in applications like radar imaging, antenna array analysis, and spatial filtering, ensuring that the essential signal characteristics are preserved. Now, my colleagues will share the solution live script, which you can use for your future references. So to conclude the today's tutorial, we saw how the signal was transformed into frequency domain using FFT function, and we also visualized its frequency spectrum. We have then implemented the FFT shift, which was used to center the frequency spectrum for clearer analysis. We then reconstructed the signal using the IFFT function, demonstrating the accuracy of transformation process. We have also seen how a 2D sinusoidal signal can be analyzed using the FFT2 function to showcase the application of Fourier analysis to spatially varying signals. Thank you for joining this session. If you have any questions, you can please post them in the chat window. Thank you for joining this session. Since there are no further questions, I will close today's session. Thank you.